Greetings from OzU Rover Team at Özyeğin University, Istanbul, Turkey. Our team, composed of 35 passionate students who are designers, engineers, and programmers, shares a common goal: building and operating rovers, meanwhile not forgetting to inspire future generations. As we celebrate our team's 10th year anniversary, we are excited to reveal our latest rover, RS2.
Our rover was redesigned with robust components. The chassis was modified to accommodate a new robotic manipulator with more volume. The rocker shaft suspension was adjusted for lower ground clearance and improved turning. Wheels were also improved, using polyamide 11 and SLS 3D printing for tank movement efficiency and reducing weight. To boost maneuverability, a dish tire design with cruiser set at a 30-degree angle was implemented. Additionally, a gyrated structure was integrated into the tire for weight and flexibility. A bicycle spoke-like design ensures the necessary flexibility and stiffness. AK-70 motors were chosen for their high torque and RPM, enhancing obstacle traversal and maneuverability.
This year, a new 5-DOF robotic arm was designed. Brushless DC motors are used in every DOF. Psychological gearboxes are designed to achieve required torques without backlash and backdrivability. Connectors and joints 3D printed utilizing carbon fiber filaments with high strength-to-weight ratio. Carbon fiber 3K tubes are used as links. The end effector implements a parallel gripping system. TPO fingers are used to increase the gripping force area. The end effector has a slip ring mechanism, allowing for infinite rotation. This allows rotational dexterity, improving maneuverability.
Our robotic control flow follows the appropriate design requirements in line with the use cases within mission tasks. Gazebo hosts the simulation of our robot upon which we build our applications. RAS Control manages hardware services with interfaces developed to control different joints. On top of this lower-level system, MoveIt calculates and sends trajectories for the joints to follow with an inverse kinematic solver. Our GUI accommodates a model of the robotic arm to give mission control visual hints while conducting teleoperation with a joystick.
As the electrical and electronic sub-team, we completely overhauled our electrical design. We significantly increased the data collection capability of our science board. The science board includes a custom-developed brushed motor controller to fit in with other systems seamlessly. We enhanced our custom-made power distribution card, Perfidia, which features the other boards. The board includes customized synchronous buck converters that can be adjusted using the other boards. Our design philosophy prioritizes ease of replacement to improve redundancy and adjust the voltage levels using the regarded daughter board. Our power electronics design are simulated to their extremes to ensure the compliance with the IPC standards. We have developed STM32 development boards that incorporate CAN-bus for seamless integration with the essential systems of the rover.
In response to the changing power requirements from our robotic arm, we changed our battery configuration from 7S8P to 6S8P. Additionally, the batteries are protected by a BMS for safer operation. Our team maintained last year's modular approach to batteries, where each series can be connected and disconnected separately with proper safety measurements in place.
For robust communication, we created a panning antenna for long-range operations. The base antenna tracks the GPS of areas with PID controller, thus ensuring a high range. Within the network, two access points are bridged with Wi-Fi and computers are routed to them with Ethernet.
This year we have taken a general look at the missions, creating a requirement netlist and application that can accommodate them. Navigation stack supports tasks with visual markers using GPS coordinates. We use a map server to track RS on a geographical map. The autonomous stack has upgraded target tracking capabilities by using custom training and deployment pipeline built upon Yellow V5. We are able to detect and localize targeted visual markers using our Z2i camera. The system design allows for ease of scaling if support for other visual markers are required in the future. ROS is used for inter-process communications. An RRT star pathfinding service draws paths, while a PID path tracing server follows drone trajectories. A state machine checks for collisions and records detected markers while moving to goals.
The science module initiates sampling with a drill that can dig 15 centimeters into Martian soil. The samples we collect go straight through a flexible tube systems to reach the sampling compartment.
We utilize Bradford assay to deduce the protein concentrations of samples. We observe the binding of protein molecules to Comassi brilliant blue dye, which results in a shift in the dye's absorption maximum from 465 nanometer to 595 nanometer, proportional to the protein concentration. CCD spectrometer allows us to graphically analyze the compounds in selected samples. RS also has sensors to measure air quality, detecting gases like ozone, carbon monoxide, carbon dioxide, methane, and formaldehyde at very low concentrations. Lastly, we have sensors to measure humidity, temperature, and light. With this data, we can gain insights into Martian atmosphere and reason the potential for water presence beneath the soil.